Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside as we jump into Chapter 5 in the Big Ideas Math Integrated Math 1 textbook. This is on solving systems of linear equations. Eventually, by the end of the chapter, we actually even do systems of inequalities, which will be super fun, but we got to start with our systems of equations, specifically with this section on solving systems of equations by graphing. So we did graphing in chapter 3, and this comes back, and some of the things we did in chapter 4, if we rewrote equations into certain forms, may help you. It all depends. I actually don't know how the problem set works as a whole. I know solving systems of equations by graphing works, and this is a good introduction to this because it's a good visual representation of what our solutions mean. So we're going to jump into that in just a moment. Now, before I begin, I want to let you know, and I mentioned this at the end of my chapter 4 test and cumulative assessment video as well. We've gone 4 chapters now solving equations algebraically, right? Subtracting this from both sides, adding this to both sides, dividing this from both sides, etc. And I say that stuff out loud, but I also write down the thing, right? When I divide both sides by -4, divide by -4, divide by -4 on both sides and cross them out and all that kind of stuff, right? I show the action. From here on out, I'm no longer going to be showing those actions. Okay, I'll go from one step to the other. 2x plus 3 equals 8. Suddenly it'll say 2x equals 5. What did I do? I subtracted 3 from both sides. Now, generally, I'll mention what I do to both sides, but I'm no longer going to show the action. And you might wonder why I'm going to do that. First of all, it's an efficiency thing, okay? Not just for me, but also for you. I want to make sure that I preach that efficiency, that eventually you want to probably avoid doing it as well. At what stage? I'm not really sure. I'd say this is probably the stage. We've gotten several chapters in it. And regarding my efficiency, I've been sitting here for the first 4 chapters going like, I don't want to do this. I don't like writing those actions personally. I don't do it. And that's kind of my number 2 thing. My IM2 and IM3 videos don't do it. Okay. At some point, we kind of lean away from it. If you've noticed in lecture portions, the book doesn't really ever do it anymore either. Every so often they'll do it, but sometimes they skip steps and I have to explain what they did from them. So if there, and you know, this will happen in my classroom as well, where if I'm doing a lecture thing, I'll have again 2x whatever plus 3 equals 8. Then I'll write 2x equals 5, and then some people go like, well, wait a second, where did the 3 go? Well, good question. Well, I subtracted 3 from both sides, but the other question is, why did the 8 turn into a 5, right? You know, so it's like those kinds of things. What happens in between? So I'll still be explaining them, but I am no longer going to be showing those steps unless I feel like I need to. So I wanted to give that warning, and I'll give the warning again for maybe 5.2 and 5.3 videos. After that, I'm just going to keep going off of it. But I'm going to go ahead and get started, guys. Sorry for the extra long introduction. If you'll go ahead and jump to the description section down below, you can download this PDF of this section, as well as we're solving by graphing. So graph paper will be provided as well. I'll be guaranteed that we're going to have to do some graphs. Grab yourself a ruler. Maybe we need a graphing calculator. I'm not really sure yet. We'll see what kinds of questions there are. And also the timestamps for the questions. There are 33 questions total. Now, there are a couple nerds behind me playing Tetris. Would you rather watch the Tetris nerds, or would you rather watch an instructional math video? That's right. This is what you're here for, kids. We're going to go ahead and get started on this one. We're going to learn how to check solutions of systems of linear equations, which actually doesn't mention anything about graphing yet. This is the very beginning portion of what does it mean to be a solution. So that'll be a pretty quick, straightforward thing. Solve them by graphing, which for us guys is going to mean where do they intersect? Where do your lines intersect? And use systems of linear equations to solve real life problems, a bunch of word problems, things. We've seen those before. So get stoked. We're going to get started. A system of linear equations, by the way, that's your first term here. It's a set of 2 or more linear equations in the same variables. An example is shown below. Now, they don't do the curly brace thing here. I'm probably going to do that every so often when I set it up, but that's just bracketing your system right here. When you see a systems of equations, you might show that. X and Y, 2 variables in 2 different sets of equations, neither of which you could solve one for in and of itself right off the bat. Sometimes you can in some situations. But with this system together, we can come up with a solution that'll work for both of them at the same time. A solution of a system of linear equations in 2 variables is an ordered pair that is a solution of each equation in the system. You have to remember whenever we graph, and that's what this is going to be about, guys. Whenever we graph these equations, x plus y equals 7, or get y by itself, or whatever, you make a line. That line has a bunch of points on it. There are ones that we plot, and they're the ones that we connect to make the line. Every one of these points represents a solution to that particular equation. An xy here, an xy here, etc. There's an infinite number of solutions, and that's what the graph represents as a line. but that's just for that one equation. This equation has another line right here as well, and that has an infinite number of solutions in and of itself for its line, but we're going to find the one solution, and there are special cases where there can be infinite or none, but the one solution that'll work for both at the same time. Is it when x is 1 and y is 7? Is it when x is -2 and y is 0? That kind of stuff we're going to find together. Anyway, let's go ahead and check solutions. So I believe they're going to start off not with the graphing itself, but understanding what a solution means. We have this, they say, tell whether an ordered pair is a solution of the system of linear equations. We have 2, 5. X is 2, y is 5. They want us to find out, does x equals 2, y equals 5 work for both equations in the system? If so, then that means it's a solution to the system. So what are they going to do? They're going to take this first equation, substitute 2 for x and 5 for y. 2 plus 5 is 7. 7 equals 7. That checks out. You substitute 2 for x and 5 for y here. Use parentheses for substitution as you multiply. 2 times 2 is 4. 3 times 5 is 15. 4 minus 15 is -11. And that equals the -11 on the other side. So both equations work for that. Therefore, 2, 5 is a solution, probably the only solution to the system. And when I say probably, I mean it is the only solution to the system there. If I tried 2, 6, it wouldn't work for either. But more importantly, if I tried 1, 6, 1 plus 6 may be 7, but 2 times 1 minus 3 times 6 might not be -11. And I'm sure this one's going to show exactly that. Part B, -2, 0. Substitute -2 for x and 0 for y in both equations here. Start with the first one. -2 times -2 is +4. Minus 4 is 0. 0 equals 0. That one works. But substitute -2 into this one. -2 plus 4 is 2, and 2 does not equal 0. So although it is a solution to one of the equations in the system, it's not a solution to the other one. Therefore, it's not a solution to the system, or it's not a solution in the system, or of the system, I guess is the phrasing they say. System of linear equations is also called a linear system. Okay, so that's the idea behind this, a basic substitution. So our first problems, no graphing, probably just plugging those numbers in. That also means we can double check our solutions, right? We can always plug them in and see if they actually do work. All right, solving by graphing. I kind of mentioned some of it, but I didn't get the full gist of it just yet. The solution of a system of linear equations is the point of intersection of the graphs of the equations. Now, that's the part I didn't mention. You draw your lines on the same graph. Wherever they intersect is the solution to the system, assuming the graphs are correct. So graph each equation in the same coordinate plane, estimate the point of intersection, and when we say that, we're hoping that these are integer solutions. If they go on like 2.75, that'll be kind of an issue. Check the point from step 2 by substituting for x and y. So they're doing a double check. I will only double check if they ask of it, or maybe just for the first couple problems, then I'll move forward, and I'll probably do it mentally at that point. But you need to make sure that it works for both. You just want to make sure you graphed it right. Okay, here are two equations in slope-intercept form. Y equals -2x plus 5, y equals 4x minus 1. They say graph each equation. Y equals -2x plus 5 is a y-intercept of 5, and we go down to right 1, and boom, boom, plot some points, draw the line. Plot as many points as you can fit. This becomes a good reason why we might want to do exactly that, because you don't know where this line is going to intersect with the other line, assuming that they do. The next one, y equals 4x minus 1, is a y-intercept of -1, and a rise of 4 and run of 1, rise of 4, run of 1. If you plot things, to their very integer cores, then there's likely a point that will, not only will they intersect, but when you actually plot the points, you're actually going to see that, hey, this lands on this spot together. Like when I go up 4 over 1, okay, I just hit that point, boom. So you know that's going to be the point of intersection, but you still complete the graphs, right? So in terms of solving the system, these intersect at the x value of 1 and the y value of 3. 1, 3 is the solution to the system. Now, when I stated understanding what a solution to a system means, this is what I mean. Our answer should be an ordered pair. An ordered pair, not x equals 1, y equals 3. It's x equals 1 when y equals 3. It's that specific point that is the solution to the system. So your final answer is an ordered pair. I need to stress that because we're not only going to solve by graphing, we're going to solve using algebraic methods in future chapters, future sections. But that's what we're going to do. Now, double checking, -2 times 1 plus 5 is 3, and that one works. 4 times 1 minus 1 is 3, and that one works. Again, we might do some mental double checking, but there it is. You can also double check using a calculator and try and see where they intersect there. We might have to do that kind of thing. But yeah, there's an intersect feature, which we'll take a look at for that. Now, as far as table feature goes, this is kind of cool. When x is 1, you get the same y value for both, and that's the point of that you get the same y value for that particular x value. Because there's more than one solution to every equation, right? But there's only one of them. that is the same y value for that particular x. Okay, modeling with mathematics. It says a roofing contractor buys 30 bundles of shingles and 4 rolls of roofing paper for $1,040. In a second purchase at the same prices, the contractor buys 8 bundles of shingles for $256. Find the price per bundle of shingles and the price per roll of roofing paper. Now, this is doing it graphically still, I imagine. I imagine we're still going to graph these ones. So with this one, we are coming up with a sets of equations. We have to define variables. It's best, really, guys, it's best to use x and y because when we graph them, we need to have an x and a y. So it looks like we're going to define price per bundle as x and price per roll as y. We've set up equations before. When you do, well, I don't know how often we have, but $30, 30 bundles of shingles times x dollars per bundle plus 4 rolls times y dollars per roll equals $1,040 in the first purchase by the contractor. And then the second one, 8 times the price per bundle, 8x, apparently plus 0y equals 256 was the second setup. So here's your system of equations. Now they said graph the equations. This has much larger scaling. So I don't know, maybe I'll use the graphing calculator for some of them, or we have to change the scaling itself. You know, it's one of the things you can get y by itself and put it in slope-intercept form or come up with the intercepts themselves. But like I said, it's just going to be a massive, actually they did that right here. It's still just going to be a massive undertaking as a whole. Now, interestingly, divide these by 8, guys, you do get the equation x equals 32, if you notice that. X equals 32 is a vertical line. We haven't seen vertical lines since the standard form equations, or at least the review section. But since the section on graphing equations out of standard form, x equals 32 is a vertical line. The easy part about that is you know they're going to intersect at the x value of 32. I mean, it's as simple as that. But, of course, we are solving by graphing, so we have to find out what y value they intersect at. So the x value will be 32, of course, because only x can be 32 here. But the y value apparently is 20 through the graph. So they do a double check. They make sure that it equals that. So now, because this one's a word problem, like I stated, solutions are ordered pairs. But in a context-based scenario, guys, word problems means our answer should be in words. Although 32, 20 is the ordered pair, we should actually state this. The price per bundle of shingles is $32 and the price per roll of roofing paper is $20. You should definitely be writing your answer as a solution set like that. Okay, that was actually a pretty quick lecture portion, all told, especially when I gave a little precursor on how I'm going to be doing some manipulations of equations. And I don't know how often I'm going to do them in this set here. One other thing I was actually going to mention, guys, is eventually we start hitting geometry in the latter half of this book. So it's going to be pretty easy algebraic maneuvering from there, and I really just want to get into the geometry aspects at that point. Anyway, guys, let's go ahead and get into the vocabulary and core concept check numbers 1 and 2. Then we hit 3 through 33 on this set. Number 1, vocabulary. Do the equations 5y minus 2x equals 18 and 6x equals negative 4y minus 10 form a system of linear equations? Explain. Absolutely they do. It's a set of more than one equation. And it has variables in it, right? In this case, do they have to say 2 or more variables? I guess. But absolutely. It has more than one equation and more than one variable. I guess it needs to have more than one variable. Otherwise, you'll never have a solution set unless it's no solution or infinitely many solutions. Even if one equation only has y in it and one equation only has x in it, at least it's still more than one variable that way, so it still works. All right, number 2, different word, same question. Consider the system of linear equations here and here. It says which is different, find both answers. Okay, let's start seeing what they say. Solve the system of linear equations. That means we need to find the point of intersection x comma y. So I imagine one of these is also going to say that. So let's call that the A. Solve each equation for y. I don't see that as the same thing. I'm going to put that as a B for now. I'm not sure. That doesn't sound the same. Because solving the system is finding both the x and y. That's the point of intersection, okay? Yeah, find the point of intersection of the graphs of the equations. That's definitely an A by solving the system. Find an ordered pair that is a solution. That's also an A. Yeah, B is different. Solving for y. That might get you on the track of graphing. Or when we use what's called the substitution method in section 5.2. Those are things you can do to start setting up solving a system, but that's not solving the system itself. Now, I just mentioned, you can use that for graphing, right? Notice how both of these equations are currently in standard form. We can also graph out a standard form, and I intend to when my intercepts are both integers. I intend to do that if they're set up in standard form. We can also rewrite that in slope-intercept form. Case in point, if you guys remember in standard form, I could divide these by -4 and boom, I'll get my x-intercept. I could divide these by 2 and boom, I'll get my y-intercept. Dividing 4 by 4 and 4 by 2, integers. I'll probably graph out a standard form with that. This one, if I divide y by -1, I'm all good. But if I divide, by 4, 6 divided by 4, fraction. I mean, it's a 1.5. It's not the worst one, but it's a decimal. It's a fraction. I would rather rewrite this in slope-intercept form, and I intend on doing that for scenarios. I will solve for y, get it in slope-intercept form, and then graph and find the point of intersection. Now, before I move forward, I know that I'm spending some time before I hit here. I do want to mention, and I'll just mention it in a big screen right here. Get a ruler. Get accurately scaled graph paper, plot as many points as you can fit. With standard form, though, use the ruler and line that up as best as possible because you're trying to find the point of intersection with this. If you plot just these 2 points and draw a line that squiggles out, you're going to intersect with something completely different beyond that. Okay. Forget the nerds playing Tetris in the background. Let's go ahead and do problems 3 through 33 right now. I'm going to go ahead and get started. Numbers 3 through 8 tell whether the ordered pair is a solution of the system of linear equations. So we're checking to see if 2, 6 is the solution for this system here, x plus y equals 8, and 3x minus y equals 0. As if to say, for this x and y, when I substitute them, do I get the left side to equal the right side in both equations? It must be both. Very quick substitution, 2 for x plus 6 for y equals 8. That's 8 equals 8, and that one checks out. Top equation. Bottom equation, 3 times 2 minus 6 equals 0. 3 times 2 is 6. 6 minus 6 equals 0. 0 equals 0. That one checks out. So, is it a solution to the system? Yes. I'm just going to put yes or no. But yes, 2, 6 is a solution. And when I say a solution, I'm going to keep stating this, guys. When I say it's probably only the solution, I'm going to tell you right now, it is the only solution. There is no other x, y that will be a solution for both equations simultaneously. Right? Each of them have infinite sets of solutions on their own, but together as a system, that's the only one solution. All right, number 4. Let's check A2. That took, give me a second. All right, we have 8-2 against the system x minus y equals 6. And mind you guys, we're not yet graphing on these ones. This is just a precursor for something we can do for any solution set. 8 goes for x, 2 goes in for y. We have 8 minus 2 equals 6. And I've stated this way back in the day, guys. Please narrow it down to this part, that last stage. We know that 8 minus 2 is 6, but actually compute that, right? Don't what's the phrase? Don't have confirmation. Oh, this should have a y in it. Don't have confirmation bias or whatever in stating, oh, it must be 6. Actually compute it. I don't know if that's the actual phrase. All right, 16 minus 20 equals 4. Well, that's, see, because someone might say, oh, yeah, that is 4. No, it's -4, right? -4 equals 4 is a no-go there. That's not the case. Let me actually put a like that. So this is a no, not a solution to the system if I calculated everything correctly. No. Number 5. And look, it's all the same, what we're doing here. Just mathing it out, but it needs to work for both. If you notice, these two are actually in slope-intercept form. No change in what you do, but y is just on this side of it. Just be careful when you do your substitution, right? -1 goes in for x, 3 goes in for y. So in the first one, is 3 equal to -7 times -1 minus 4? -7 times -1 is +7. 7 minus 4 is 3. That one's all good. Top equations have been supreme. By the way, if the top equation's wrong, cut it. You're done. Right? So they're making us do more work if this bottom one's wrong. Why didn't they have the bottom one on top? That kind of thing. So yeah, this one's 3 equals -8 plus 5, or 3 equals -3, which is not so. That one's an example of no. Yeah, if they had the bottom equation on top, the moment I saw that, I would halt the problem. I'm done. I say no, it's not a solution to the system. If it's not a solution to one of them, or either of them, but just one of them, it's done. Number 6. Notice I'm doing my curly brace thing here. I got some ugly curly braces going on. I'm the master of pretty curly braces, so I'll try a little bit harder next time. Students always tell me, I'm jealous of how you can do that. You make it so pretty. That one's hideous right there. All right, -2 equals 2 times -4 plus 6, or so we imagine. We should really put the question mark. Is it? Is it? It is. So that one's all good. Let's check this one. -2 equals -3 times -4 minus 14. 12 minus 14. -2, that's right. Oh, look, that's that -2 as well. So it's good to get a yes back there again. Yeah, I've decided. So look, I'm looking down below. See where it says check your solution. I've decided I'm probably going to do it mentally. Unless it's really robust kind of work that you have to do on them. Because these are the problems that I'm showing you all the work on what you're actually checking. So I hope that's okay. I hope that makes sense on how or why I do that. Because I'm going to trust my own graphs more than anything else. And I'm going to mention more things about that when we actually get to the graphs. Oh, I was not consciously trying to make a prettier looking curly brace. That one's a little bit better. Not my best effort. All right. Back to standard form equations, and ones of which I would never want to graph that. Well, I never want to graph that one to begin with, to be honest. All right, 6 times -2 plus 5 times 1. That's -12 plus 5, and that is -7. So far, top equations, like I said, they've been panning out. Bottom equations, on the other hand, have had their instances of not working out. Let's see this one. This one, however, looks to be good. -4 minus 4, and that's -8. Left side equals right side for both. Yes, this is a solution to the system. Oh, absolutely. No doubt about it. Number 8, I'm actually hoping to get one where the top equation doesn't work so I can say, abandon ship, you're done. Let's see if number 8 is exactly that. Because after this, I'm only expecting that I'm going to get the right answer for myself, so you won't see any other instances of no. You know what I mean? So 6 times 5 plus 3 times -6 equals 12. Oh, wait a second. What am I doing? I copied down the problem first. In fact, let's curly brace this thing up. I mean, it's okay. My students can't do it. So, I'm one step ahead of them on that. All right, let's see. 6 times 5 plus 3 times -6. I think I'm better when I'm not consciously aware that I'm doing it. All right, that's 30 minus 18. So this one's going to work out. We get 12 equals 12. That's a shame. I actually wanted the top equation to not work. But you get what I'm saying, right? If this says 13 equals 12, it doesn't work. Done. No, don't even bother with the second one. Because automatically, once one doesn't work, then the other doesn't work. Plus -6, I'm just going to state right there. That's not really a required thing to do, but just substitution-wise, right, adding the negative. So this becomes 20 minus 6 that way, and that becomes 14 equals 14. So this one does pan out. That's another yes, and we're all good to go. So whenever we solve these ones, guys, again, I'll just do mental double-checking. I guess that's the idea behind how I want to make these things happen. And away we go. Well, I guess we're not graphing these ones, so here we go. Numbers 9 through 12, it says use the graph to solve the system of linear equations, check your solution. So they're doing a nice progressive flow on these problems. And actually, I really don't have anything to copy over on these ones here. You know, I'll let the problem speak for itself on what it is. I'll state which equation goes to which line. But from there, they made the graphs. They made the graphs. So if anything for us, it's just a double check. I mean, the left side will equal the right side because they graphed it, right? This isn't error analysis. This isn't the questions where they say, tell me what was wrong. So they're right on this. But anyway, x minus y equals 4. Okay, let's say that we graphed this out of standard form. Your intercepts would have been an x-intercept of +4, and y you would have had to divide by -1, and y-intercept would be -4. So that's going to be this graph right here. So that's you plot those 2 points, you draw the line through it, boom, there's that line, right? The next one, I probably wouldn't want to do standard form, even though the y-intercept would be 1, the x-intercept would be 1/4, and that's no fun. I'd rather subtract that 4x over, and it would say y equals -4x plus 1 like that. So from here, I would start with a y-intercept of 1 and go down 4 over 1 like that, and down 4 over 1, and then I draw that line. And you can see then they end up intersecting, boom, right there. That's the point of intersection. The x is 1, the y is -3. So for me, guys, I don't really have much to write. Again, I'm not copying down the whole problem unless I have work to show. I kind of had work to show right there, so I'll leave it. But my solution is going to be 1, -3. Now, we have to double check. Our double check is, you know what? I will show this one because the subtraction. 1 for x, -3 for y, like that. 1 minus -3 is 1 plus 3. That's what I wanted to show. And that's 4 equals 4. And then on the next one, 4 times 1, which is 4, plus -3, which is -3, is 1. So that's 1 equals 1, and that one checks out. So yeah, I probably will do most of those mentally here on out, but they said check your solution, and that one's it. Excuse me. Number 10, when it comes to graphing this one, I think the same thing. X and y intercepts are each 5. X equals 5, y equals 5. If you remember, for intercepts, you set the other variable equal to 0. It goes away. So boom, that's going to be this graph right here. We'd plot these 2 points technically right there, and we draw a line, use a ruler. This other one, y minus 2x equals -4. You could get the x and y intercepts, but for the sake of window range, well, for the sake of window range, you can't see the y intercept either. But if I add 2x over, it's y equals 2x minus 4. So the y-intercept's -4, and we go up 2 over 1, up 2 over 1, up 2 over 1, and eventually you land on this point right here. But, you know, you keep going. That's 3, 2. So point of intersection for this one is 3, 2. And again, I'm just putting that. Let's do this one mentally this time. 3 plus 2 is 5. 2 is for y first. So 2 minus 2 times 3, 6. 2 minus 6 is -4. That equals -4. Okay. All right, number 11. 6y plus 3x equals 18. If I were to do, if I were to do intercepts, again, their window range is a little funky, so I'm just going to state which graph it is, although we can't see the entire graph. If I were to do standard form graphing, x-intercept would be 6 divided by 3, y-intercept would be 3 divided by 6. So that looks like it would be this one here, the y-intercept of 3, boom, x-intercept down here is 6, that's this line. This one, again, x-intercept would have been -24. This is an example where I would probably just get the y. I'd just get it in slope-intercept form. Divide by 4 on both sides. You get a y-intercept of 6. You get a slope of up 1 over 4 or down 1 left 4 as well, and that's where we hit that point. But anyway, that's this line here. We'll do those when we do the actual graphs, right? So what's the ordered pair? -4, 5. And again, you may think I'm over-speaking on the problem itself with regard to the objective. I am. But I want to make sure that you're understanding how we will do the graphs when we hit them. So -4, 5, plug it in. 6 times 5, 30. 3 times -4, -12. 30 minus 12, 18. That equals 18. -4 for x. Opposite of -4 is 4. Plus 4 times 5 is 20. 4 plus 20 is 24. That equals 24. All right, number 12. 2x minus y equals -2. That x-intercept would be -1. Y-intercept would be +2. So that's going to be this graph here. Boom, boom. 2x plus 4y equals 8. X-intercept is 4. Y-intercept is 2. Okay, dividing by 2, dividing by 4. So x-intercept is 4. Y-intercept is 2. They have the same y-intercept, therefore that's where they cross and they intersect. So remember, they're only intersecting at one point together, right? That is the one solution to the system. And it doesn't appear, maybe it's later, it doesn't appear that they have special cases, no solutions, infinite number solutions. You might know what's going to make those things arise. We'll see. Anyway, let's double check those. 2 times 0, hey, both of these are 0 either way. 2 times 0, all right. -2 is -2, plus 4 times 2 is 8. Yes, those both work out. All right, guys, those are the ones that we did without graphing ourselves. Now, I believe, yes, we are going to graph ourselves. So get that graph paper ready. I'm going to get it ready as well. And I will write down the problems because I may need to do extra work on them or not. We probably have some work to do on them. Maybe, maybe not. Either way, let's write down the system. All right, y equals -x plus 7. Well, you know what I'm going to do, actually? I'm going to color code these graphs. So this one I'll make blue. This one I'll make green. I'll default to blue on top, green on bottom, if I forget to actually color code those as a whole. So these are in slope-intercept form. I have a y-intercept of 7 and a slope of -1. Now again, plot as many points as you can fit because this one will intersect with the other one somewhere, and we want to find out where that thing is. But complete your graph first before I move on to the next one. So with this one here, I have this line, right? with an infinite number of solutions on the line itself. But which one does it share with the other graph? Y-intercept of 1 and a slope of 1, up 1 over 1, this time to the right. So boom, right there. Now don't stop, right? Just go ahead and continue the graph, please. I know that we landed on our point of intersection, but might as well just get your graph practice on, even though this is the most number of points you're going to plot. Hey, if I'm doing it, why not you, right? Pretend like you didn't know what the other graph looked like yet. Okay, so that's this guy right here. Okay, so together, and by the way, I have arrows on my graphs. I mean, it's by my line tool, but I have arrows on my graphs here. So here, and do they say check your solution? They don't say check your solution, so I'm going to go ahead and not check it. But the ordered pair is the point of intersection. That is 3, 4. We can double check this one. 3 plus 1 is 4. Negative 3 plus 7 is 4. Okay. All right, but hey, guys, that's the answer, right? Ordered pair. Ordered pair. Okay, number 14. Also slope-intercept form. Well, the first 4 are slope-intercept forms. So, and after that, we get some standard form stuff. So I'll decide whether I want to rewrite it in slope-intercept form or leave it as is. But I got y equals negative x plus 4. Ugly curly brace again. And y equals 2x minus 8. Can I fit that right? If I squeeze it in. All right. Negative x plus 4 looks like, again, a lot of plotting points here, but down 1, right 1, and up 1, left 1. So we get the points. Now, I want to mention this here. I don't anticipate they're going to do this, but I'm just going to go and start stating it right now, okay? I mean, this might apply to my classes only, but we'll see how it works in the book. Now, first of all, my point plotting was really, really bad here. But, sorry, I have to think while talking. When there are other ways you're going to learn to solve systems of equations. You're going to solve them algebraically. And by solving algebraically, that means that any kind of solution that you have is feasible. That includes weird decimals, weird fractions, things like that. Solving by graphing has its merits. One of them is understanding what it means to be an actual solution, why we write our answers as an ordered pair, the point of intersections means, things like that. Special cases as well will also make a lot of sense. But we're also hoping that we land on integers, integer values such as this one. And this one, by the way, is 4, 0. And I know I'm speaking on a bigger general thing other than just this one particular problem, and I'm going to keep moving forward as I talk through them. So number 15, we're going to keep moving forward. But I'm only hoping that these sets of problems that they give you don't land on decimals. I mean, the book mentioned estimate your solution, right? Determine for yourself where you believe they're intersecting through. But if the book gives you good problems, then they're going to land on integer values. Otherwise, it's up to us to do a little bit of estimation. And there's reason to know when it's hitting the halfway mark versus a third mark or something like that, I guess. But if both of the x's and y's are fractions, that's going to be one of those big no bueno things. That's not saying you can't have solutions which don't have fractions, but for the sake of graphing ones, I'd probably, by the way, this was supposed to be green. For the sake of graphing ones, I'm really hoping they give you integer values. So my own statement to my students would be this when it comes to test, by the way, y-intercept of 2 and slope of 1/3 up 1 over 3. My statement to students will be this. If you're asked to solve by graphing, expect to get integer solutions to both x and y of your system. Not only that, expect them to fit within your window range. If neither of those things apply, then you probably graphed wrong. And that's why I want to bring all that up. I'm not bothering double checking. If for any other reason, then I believe if I made a mistake, you would see it outside of the window range, or you would see it land on non-integers. So if I land on a non-integer solution set, I'm going to raise an eyebrow and say, I might have done something wrong. This one is a y-intercept of 5 and a slope of 2/3. So up to right 3, you can tell that it doesn't actually hit going this direction. But if I go down to left 3, hopefully it hits. And hopefully it hits on integers. So down to left 3, boom. I was sweating bullets right there. I wasn't sure if it was going to hit, but there it seems to hit on that one. But that's my point I want to make one more time. Now, there was a word problem set where it looks like we're going to have to change our window range when it comes to overall scale, and I get that. But I mean, if it was a general case kind of thing, and they give you graph paper on the test, and it goes from -10 to 10 for both x and y, that kind of thing like that. By the way, this point of intersection is -9, -1. If it does give you that, number one, when it comes to solving for graphing, expect integer solutions. I mean, can there be fraction ones? I guess. I don't intend on making my own test questions that would have those, unless it was algebraic problems, in which case that's still kind of cruel. I mean, it's good to just work on the methods rather than make them too extreme. But number two, we want to make sure it's within window range. If they don't intersect within your window range, now here's the main thing that happens if they don't intersect within the window range. Here's the main reason someone would get that wrong. Your negative slope, you accidentally graph positive, something like that. Because if it doesn't fit in the window range, how are you going to see the point of intersection? Right? That's the point I want to make on that. Anyway, I spent 2 problems just talking about that one thing on understanding what kinds of problems that you'd be presented without the problem makers being too barbaric. And I think that's something we can expect. Anyway, negative 4 y-intercept, rise of 3, run of 4. Now listen, I've chastised textbooks for progressing into something way too hard, way too difficult, way too suddenly. Even for myself, I'll go, gee, I don't know the answer. But, I've done that before and said, well, that progression doesn't really seem right for the situation. And maybe that'll happen on some of these problems. And that's part of what the solution guide videos are for. It's maybe you understand how to do every problem but that one. And I hope I can help you with it. Now, this is an example of something where I got to be careful. This y-intercept is 11. That is a little bit out of range. That's something where I generally caution myself. But it is just 1 above 10, which I guess is... This hits right to what I said about if it's out of window range. Uh-oh. I might have to change my window range here, guys. All right, let's see how this one works. Down 1 over 2. Okay, we might run into trouble here. Down 1 over 2, down 1 over 2. Oh, no. Oh, no. Guys, we're running out of window range there. Okay, let's make a best guess extrapolated figure to this. This is at the point 10, 6, right? If I go down 1 over 2, then this point is right there. Now, that point is, because I'm imagining this is my point of intersection. I'll talk about it in a bit. That's at 5 for y and 12 for x. So 12, 5. Take a look at this one in blue. Oh, by the way, let me draw the green line here. Oh, I did not know this was going to happen. Good thing I just talked about this stuff. I wouldn't put this on a test unless I had the scaling go out to that direction, because that's kind of cruel, right? It's a little unexpected. Anyway, I do have arrows. Assume I have an arrow on that right side that cuts off the screen. Okay, so over here, this point was at 8, 2. I need to go up 1, 2, 3 to 5 and over 1, 2, 3, 4 to 12. Yes, it's going to hit that same point. So my point of intersection, a little out of reach, and I didn't know that was going to happen, but it's 12, 5. This is one of the cases where, although I'm trusting that my count is correct, maybe we should double check. Let's go and plug them in and see how it works. Now, this is what I also might want to write down because that is fractions. So 5 equals 3/4 of 12 minus 4. 3/4 of 12, you might know, is just 9. But 12 divided by 4 is 3. 3 times 3 is 9. And 5 equals 5. That one actually checks out. So that one's good. I'm imagining the other one should be good, but we'll make sure. 5 equals negative 1/2 times 12 plus 11. Half of 12 is 6. Opposite of that is negative 6. Negative 6 plus 11 is 11 minus 6, which is 5. So 5 equals 5. That one checks out. That's a good reason I might want to double check something that's out of window range. Now, what's something I can do to fix that? I can get larger graph paper. I can change my scales. I can... those are really my 2 options when it comes to solving by graphing. Okay, let's move on to number 17. We have equations in standard form. So we have... Now, in standard form, I'm going to look to graph out a standard form when the intercepts are, again, not fractions and in window range between negative 10 and 10, or at least reasonable window ranges. The top equation maybe doesn't necessarily give us that. If I divide both sides by 9 to get the x-intercept, I'd get negative 1/3. That's not something I want. So I'd rather rewrite this one in standard form. So I'm going to subtract 9x from both sides. And then I divide both sides by 3. We'll get y equals negative 3x minus 1. And by the way, I mentioned this at the top of the video. I'm no longer going to be showing the actions in between what's happening here. Meaning, I subtracted 9x. I'm not writing minus 9x, cancel them out, things like that. I'm just going to do it. Divide by 3. I'll state it out loud. Divide by 3. Boom, boom, boom. And here's that equation. That's not the answer, but that's what I'm going to graph. That's what I'm going to graph. It is a fraction x-intercept, so I won't graph out a standard form there. This one, I will graph out a standard form. If I divide by 2 Negative 4 divided by 2, I'll get my x-intercept of negative 2. If I divide by negative 1, I'll get my y-intercept of 4. Let's remind ourselves how that works. Set the other variable equal to 0, divide by whatever number's in front. That includes a negative 1. So those points I can plot. And let's get graph paper for that. But those points I can plot, and then I can draw a line through them. Now, slope-intercept form is probably the one you're better off with for these, for the most part, only because you're probably more inclined to plot as many points as you can fit. Whereas, and I'll do this one in blue and this one in green. Whereas, for the other one, you're probably only inclined to plot the intercept points. And then if you don't do your ruler stuff very well, then that might be an issue. So with this one, I got negative 3x minus 1, like so. And then on the next one, we have an x-intercept of negative 2 and a y-intercept of 4. So here and here. And this is where you kind of do your press your luck. I mean, it looks like I can tell which points they're going to go through. But, I don't have a ruler, so I got to first draw my line tool, and then I'll extend it out like I do have a ruler. But you can see here, we're only doing the best we can with the line. Did it actually continue on the proper slope with this thing? It depends on how well you did with that. But at least you can see where it looks like they're actually hitting together, which is negative 1, 2. And I'm not going to question it. I believe that's the answer there. But, something you can do with the standard form is even if these are the only 2 points you plotted, you can say, well, it did go up 4 over 2 or up 2 over 1. So you can continue your slope after that. Some people may argue at that point you might as well rewrite it in slope-intercept form. Some people aren't good at it, so it just depends, right? But looks like my line was still good based off that. Negative 1, 2 is the solution to the system, even written in standard form. Number 18. Okay, number 18's bottom equation is interestingly different. Do you remember how those ones work? But the top equation, this time when I rewrite stuff like this one, I'll rewrite it in blue already, so we know that we're talking about this one here. My x-intercept, I divide by 4 from both sides when setting y equal to 0, and I get 5. My y-intercept, I set x equals 0 divided by negative 4, and I get negative 5. So those are the points I'm going to plot on that one. Y equals negative 5 is just that equation, 0x minus 5. Slope of 0, crossing at negative 5 horizontal line. So let's get it done. Top equation, x-intercept of 5, y-intercept of negative 5. That also means the slope of negative 1, down 1 over 1. Boom, 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 right? So you can tell it's kind of doing a lot of that. So it'll also go up 1 over 1 here, all the way through like that. I'm just going to draw it like that one. Y equals negative 5. I mean, here's the thing. I mentioned this in the lecture portion. That means the solution to the system will have a y value of negative 5, because what else can it be? But it's going to be a horizontal line as well. If there's one reason to know whether y equals negative 5 is a vertical line or a horizontal line, know that the y value has to be negative 5. So the only way that's possible is if it's a horizontal line. Where do they intersect at? 10, negative 5. And again, the y value is indeed negative 5. I'm going to trust it. Looks pretty good. We're going to move forward. Number 19. X minus 4y equals negative 4. Good for standard form. And negative 3x minus 4y equals 12. Also good for standard form. As long as I have integer values that fit within my window range. My x-intercept here will be negative 4 when we set y equal to 0. My y-intercept, I divide both sides by negative 4, and I get 1, positive 1. Here, for this guy, I get an x-intercept when I divide by negative 3. I get negative 4 for x. Divide by negative 4 for y, I get a y-intercept of negative 3. Okay. It looks like I already know the answer based off the fact they share the same x-intercept. So I'm guessing it's going to be negative 4, 0. But we graph them anyway. They said solve by graphing. Not solve by sheer luck. All right, x-intercept of negative 4, y-intercept of 1. It's the top equation. So I'm going to kind of track this slope, right? Down 1 over 4, down 1 over 4, kind of like that. Just to make sure I'm kind of hitting it right. Looks pretty good. Oh, no, it doesn't. But I know where they're intersecting, and I need to plot it more through that point. The other one, x-intercept of negative 4, hey, hey. Y-intercept of negative 3, hey. And that's like a down 3 over 4. Yeah, down 3 over 4 kind of scenario. So I could like track it. I go up 3, left 4, you know, maybe get it started right there and make sure it's still going down 3, right 4. So you can still do, like I said, even if those are the only 2 points you plot, you can still kind of line it up with how the slope would go and all would be good there. Now, they need to hit at the point of intersection, the solution to the system, and it's going to be that one there, which is negative 4, 0. What I expected all along. Number 20. The first equation does not lend itself well to getting my x-intercept, because dividing that by 4 would give me a fraction. So I'm going to rewrite this one in slope-intercept form. The bottom equation I think I'm good with in standard form. This one I can subtract 4x from both sides and then divide everything by 3. So I get negative 4/3 x and then plus 1. And that's fine, right? We can have a fraction for our slope. I just don't want a fraction for my x-intercept. Oh, I should have done that in blue. Oh, not everything in blue, though. Just this guy right here. All right, this other one I'll do in green. This one in green, x, y-intercept seem fine. The x-intercept is negative 6. The y-intercept is negative 2. Okay. Okay. So the top equation, or the blue equation, 1 and down 4, right 3. And then up 4, left 3. Like that. Okay. This other one, x-intercept of negative 6, y-intercept of negative 2. If I were to guess, it's going to hit that guy right there. Let's just see if it shall get close enough to that idea. I think so. Now, am I really guessing? Probably not. Again, they're probably going to give us integers, but you know, this also goes down 2, right 6, which also means down 1, right 3. So it should hit that. Without me actually double checking, that is in a solution of 3, negative 3. They didn't ask us to double check. I mean, you know, it's not one of those things where I feel like I have to. All right, let's go to the error analysis. Let's see where they wrong themselves in this set. Describe and correct the error in solving the system. So we have x minus 3y equals 6 and 2x minus 3y equals 3. They cross at 3, negative 1, so the matter of the problem will probably be in one of the graphs. So we have to see where they messed up on their graph. So let's start to explore number 21 with that in mind. X minus 3y equals 6 has an x-intercept of 6 and a y-intercept of negative 2. And that first graph seems to have that. So that one right there I think is good. The next equation, 2x minus 3y equals 3. I don't want to use standard form because of the x-intercept, although, you know, I guess it's possible. But if I subtract 2x from both sides and divide everything by negative 3, it becomes a positive 2/3 and a negative 1. So that graph seems different. This goes up 2/3, but it has a y-intercept of negative 3 instead of negative 1. So that one's graph is wrong. The bottom equation, the second equation, has a y-intercept of negative 1 instead of, sorry, has they have a y-intercept of negative 3 instead of negative 1 in their second equation. So do I know that they put in slope-intercept form? I don't know, maybe. By dividing by negative 3, then this would turn into a negative 1. So I don't know. I guess there's that. So let's fix it, right? We have the two equations. So on this graph set, the top equation was actually good. But in redoing it, because we have to find out where it intersects with the other one, we're going to have a line that looks like that. All right, the other one has a y-intercept of negative 1. I guess it's going to intersect down in this third quadrant over here. So, yeah, we can go up 2/3 and all that jazz over here, but it's going to go down to left 3, and boom. That's where it looks like it's going to hit right there. Like so. So, there you have that guy. Or ish. Ish. So, the intersection, point of intersection here, didn't expect them to graph it wrong. That seems more like a chapter 3 thing, right? Is -3, -3. Now, we could have double-checked this. We could have double-checked 3, -1, and it actually would have worked for the top equation, but it wouldn't have worked for the second equation. You get 3 plus 3, excuse me, 6 plus 3 equals 3? No, 9 doesn't equal 3. So, double-checking this one, it should work out. Let's go with it. Okay, number 22. The solution of the linear system, y equals this and y equals this is x equals 2. Knowing that they generally only get one part wrong in their error analysis, I'm going to assume their graphs are actually correct. Because the thing I'm seeing incorrectly is right here, this x equals 2. It's not that they don't intersect at the x value of 2, but you also need the y value. The ordered pair is needed. An ordered pair is needed for a solution to a system of equations. So, 2 might be the x, but the y value is 3. So it's not just x equals 2, it's 2 comma 3. And also don't put x equals 2, y equals 3. It's kind of a, x equals 2 when y equals 3, right? And that's how we do that. Put the parentheses, x first, y second, all that. Syntactically, let's make it right. Okay, numbers 23 to 26. Use a graphing calculator to solve the system of linear equations. Now, what's interesting about this is, I mean, I could do it without it too. Not with the decimals. No. I'd do things with the decimals. Like I could divide the top equation all by 0.2, and I'd get x plus 2y equals 20. Oh. Maybe it goes out of window range as well. And I could divide these by 0.6, and I think that would be fine. That's negative 20. I guess, yeah, I guess they go a little out of window range either way. So, okay, let's go to the graphing calculator for these things. So for graphing calculator, and that means we have to play with window ranges as well, right? So my first equation will be 0.2x plus 0.4y. Oh, hold on. To graph these as well, we got to get y by itself. So there's a little more work for us to do here. So on this first equation, I thought I selected blue. Let's get y by itself. 0.4y equals negative 0.2x plus 0.4. So when we divide everything by, plus 4. So when we divide everything by 0.4, this is where, again, I'm not really going to show the work, but negative 0.2 divided by positive 0.4 is actually negative 1/2. Negative 1/2 x. And 4 divided by 0.4 should be 10, because 4 divided by 4 is 1. So negative 1/2 x plus 10 is my belief on that equation. So even if we're graphing using a calculator, the calculators I have only do it when y is by itself. So like I said, there's still more work to do on this problem. Could I graph that on my own? Absolutely. Right? I'm good on graphing that on my own. But no, looks like they're going to say use the calculator. So, oh well. Maybe they're just forcing you to do it. Divide by 0.6, and I'm going to get y equals, that's 1x. And then 3 divided by 0.6, is, oh my gosh, why am I having trouble? 5, negative 5. Right? I think so. I'm going to go ahead and state that that's what that is. Okay, so those are the two equations. So let's do that again in the graphing calculator. We'll have negative 1/2 x plus 10, and then x minus 5. I will double check this, maybe. All right, if I go to graph right now, my default window range is right here. Is it perfect? It should be enough. I need to find out where those two intersect. Now, we have an intersect feature. When I hit second and trace here, option 5 is intersect. So I'll hit this 5. They say first curve, and you can see it blinking up here. This represents the first curve right there. I can hit up and down to select different curves if I want, but I'll make this the first curve. Second curve, yes, that will only have 2. Guess, well, there's only 1 point to intersect, so I'll just hit enter, and it should be right there. That's at 10, 5. So my point of intersection here is 10, 5. I'm not going to actually graph itself if the graphing calculator will take care of it, but using that gets it there. Okay, number 24. So yeah, guys, we're going to have to get y by itself on these ones to work this thing out using the graphing calculator. And maybe we have to change our window range. I don't know. That was close. That was right at the end. Negative 1.6x minus 3.2y equals negative 24. And 2.6x plus 2.6y equals 26. Okay, so for the first equation, add 1.6x to both sides. Divide both sides by negative 3.2. So 1.6 is half of 3.2. So once again, that's a negative 1/2. We're dividing by negative. 24 divided by 3.2. Well, 24 over 32 is 3/4. So this is 30/4. Oh my gosh. 7.5 plus 7.5. I'm going to go with that. I'll box them so I know which one I'm writing later. On this next one, if I subtract 2.6x from both sides and then divide everything by 2.6, 2.6 over 2.6 is 1, so I get negative 1x there. And then that's 10, right? 26 over 2.6, that'll be 10. So there's that equation. So let's see how this one works. This would be a good time when we're solving by graphing to get decimal answers. Not like repeated decimal answers, but like a 0.5 answer. And that might happen here with that 7.5. I don't know for sure. Negative 1/2 x plus 7.5. And then this other one I have negative x plus 10. Let's see where this one goes. So I have this first graph here. Okay, let's see where those two intersect. Just hit enter a few times, it'll pop up. All right, it's all good. So at 5, 5. And I don't know if I should trust the answer, but I mean, they're integers. That sounds fun for me. So 5, 5. This is a solution guide video. Did I get it right? As long as 24 divided by 3.2 is 7.5. Listen, I have a calculator. I don't know why I'm not double checking that. So I'm going to... That should be right. 32... Oh, hold on. 24 divided by 3.2. Yeah, it's 7.5. Okay. All right, I'm feeling better about things. Let's move forward. Number 25. Negative 7x plus 6y equals 0. At least it's not a decimal. The bottom one has one, but that's okay. So we have negative 7x plus 6y equals 0. And alongside that, 0.5x plus y equals 2. Okay, with this equation, I add 7x to both sides and then divide both sides by 6. I get 7/6x. On this bottom equation, I just subtract 0.5x from both sides and I get y equals negative 0.5x plus 2. Now, if I were graphing myself, I'd write that as negative 1/2 x. I'd rather use my slope as my rise over run, my fall over run. This is on a calculator, so it's not going to matter if you write negative 0.5 or negative 1/2. It'll do the same thing. So using the calculator, the decimal's fine. Totally works. As long as it's not a repeated decimal set. So let's go and take a look at that one. 7/6x, straight up like that. Boom. It's going to treat that order of operations right. And negative 0.5x plus 2. Where do these intersect? That's 7/6x up 7 over 6. And right there. Is that at... That might be at a decimal. 1.2 and 1.4, and those sound exact, and this is where graphing using a calculator is, I guess, okay. Excuse me, solving a system by graphing is okay when you get to use a calculator. Not going to double check it, but sounds good to me. That's number 25. Number 26. Get a couple decimals, but as long as we're letting our graphing calculator do the thing, it's cool. We just got to get y by itself. Now, are there graphing calculators where you don't have to get y by itself? Yes, especially online. There's Desmos. But I don't know what you can use on a test. I don't know if you can use a Desmos app or something like that. There's GeoGebra. And there's your phone. Whatever apps you have on your phone. There's Wolfram. There's a bunch of different things. So if I subtract 4x from both sides, what am I doing? If I subtract 4x from both sides and divide everything by negative 1, then all the signs switch. So 4x minus 1.5. On this one, if I just subtract 2x from both sides, I get y equals negative 2x plus 1.5, like so. 4x minus 1.5, negative 2x plus 1.5. Okay. We didn't seem to have to go out of the window range. I don't think we'll have to here as well. Yeah, no. I think that's a decimal as well. 0.5, 0.5. Okay. So that's how those features work, or 1/2, 1/2, whatever. But 0.5, 0.5. Okay. Hopefully you picked up on that, or you weren't assigned the problems. Numbers 27 and 28 say modeling with mathematics, maybe more. You have 40 minutes to exercise at the gym, and you want to burn 300 calories total using both machines. How much time should you spend on each machine? So we have two different equations that we can write. One is a minutes total, one is a calories burned total. So on number 27, and I'm going to define variables. I'm going to choose this x and y stuff just so I can get these things solved by graphing. If they seem out of window range, I'm going to use the graphing calculator to continue making the graphs. Okay. So with the first equation, let's see, elliptical trainer has 8 calories per minute, stationary bike has 6 calories per minute. Let's have x and y. It says how much time should you spend on each machine. This is where you want to start defining variables. And I just realized this is systems of equations. This is where we'll have a lot of word problems where you should define your variables here, whether you're doing graphing or algebraically. Let's let x equal amount of minutes time on elliptical trainer. This is in minutes. And y equal time on bike in minutes. So we have two equations we can write. Okay, the first equation in my system, will be x plus y equals 40. We have 40 minutes total. Time on elliptical plus time on bike equals 40 minutes of time. The next one is the 8 calories per minute that you burn times the number of minutes that you're on it. So 8 calories per minute for elliptical and 6 calories per minute on the bike. Oh, I should be using the elliptical more. Equals 300 calories burned total. That's your system. All right, that's your system. Now, even if I wanted to solve by graphing myself, manually, right? Whether you slope-intercept form, standard form, whatever. My intercepts are 40 and 40. Those are out of window range. So unless I'm changing my scale on my thing, And this one would have a y-intercept of 50 and an x-intercept of a decimal. So I'm going to I'm going to use my graphing calculator for this one, which does mean I would like to get my y's by themselves. Now, this will require, I'm going to have to change my scale on my x and y stuff. That's okay. But just, prepare. So I divide by 6. Negative 8 over 6 is negative 4/3. Now, is it required we reduce a fraction if we're going to use the graphing calculator anyway? No. But I divide that by 6, and that's what we have. So these are our equations. If I graphed on by myself, I'd do that. I'm going to use the graphing calculator. I hope that's okay. I don't want to mess up on where they actually intersect. And maybe that's why they wanted us to do those problems beforehand to get us prepped. So let's go ahead and do this one. Y equals negative x plus 40. And y equals negative 4/3 x plus 50. Now, the thing I stated already is we're going to have to change our scales. We might as well go at least 50 on x and y. And here's the thing. I don't care about the negative x's and negative y's. I only care about positives. So let's go to 50 and to 50 out. It changes my scales, but at least it'll show where they intersect. So here's a line for the first equation and a line for the second equation. And boom, they intersect somewhere there. Now, this is also why you wouldn't want to do this with a change in scale and graphing. I can't tell what that is. So my calculator can. It's a computer. So it can find the point of intersection there. 30, 10. So solution set is 30, 10. But that's not how I'm going to write my final answer. 30 is x, 10 is y. We want to represent that as time on elliptical and time on bike. So to exercise for 40 minutes and burn 300 calories, and that's exactly 300 calories. You could burn more if you just stay on, the elliptical. But if you want to burn exactly 300 calories and, you like biking and stuff as well, you should spend 30 minutes on the elliptical trainer and 10 minutes on the bike, stationary bike. That's the answer we're going to put, right? So right there. So setup, solution, done. Okay. Number 28. We're actually almost done, right? We go to 33. Modeling with mathematics. You sell small and large candles at a craft fair. You collect $144 selling a total of 28 candles. Where's my black? Speaking of which, it is number 28. How many of each type of candle did you sell? Okay, if it wasn't obvious what I did for defining variables before, first of all, I used X and Y. So when it comes to graphing, we can work that out. Your definition for variables is for the things you don't know. The thing that they ask the question on helps you for that. How many of each type of candle? There's a small type of candle and a large type of candle. So X will be small candles, Y will be large candles. But the other part, if you noticed, I was being very specific. I don't say let X equal small candles, because what are we saying about the candles? Is it how many? Is it their cost? Is it their height? Is it their burn rate or melt rate? Whatever the thing is. What is it specifically about them that we're saying? How many of each type? So this is amount, number of. Be very specific so you know this isn't a requirement for the problem. This is a strategical advantage that you give yourself when it comes to writing your equations. This is number of large candles. And I'm going to say this, listen, I say this to my students all the time, but what do they say? X is small candles, Y is large candles, but they're trying to find out the weight of them. And then they don't know what they're doing with their equation. So, by the way, we're going to create two equations. One equation will be based off the total money. The other equation will be based off total amount of candles. I'm going to start with total candles. That's generally the easier one to do. X plus Y equals 28. How come? Number of small candles, boom. Plus number of large candles, boom. Equals 28 total candles. That's a candles plus candles equals candles equation. The next equation is money. $6 per, that's a large candle by the way. $4 per small candle times the number of small candles is how much money you made out of selling small candles. Plus $6 per large candle times the number of large candles, boom, equals 144 total dollars. This is dollars plus dollars equals dollars. Okay. Now the top equation, again, this would have been out of our own window range, so using the graphing calculator is very much justified as we write that equation, getting y by itself. Getting y by itself here involves subtracting 4x from both sides and dividing everything by 6. Oh, I almost showed that. I wasn't going to show that anymore. You've gotten me in the habit of showing that now. Dividing everything by 6. Negative 4 over 6 is negative 2/3. 144 over 6, that's 24. 24. So let's get these ones in and let's get a good favorable window range for ourselves. So we'll have negative x plus 28. Y equals. And y equals negative 2/3 x. Plus 24. And these things tell a story. They're about the number of large candles. The number of large candles is 28 minus the number of small candles. And there are things we could say about these. I don't need quite as large of a window range this time. We can go like to 30 and I think we'll be safe. I don't know for sure, but let's take a look. If we find out where they intersect there, then we're good. Oh yeah. Oh yeah. If I were to guess, it said the 30, right? Is that about 2/3 of the way through? Maybe 10, 20? I'm going to guess it's 10 and 20. Let's see. Intersect. Boom, boom, boom. 12 and 16. Wasn't even close. All right, so 12 and 16. 12 is number, and here's the other part where it helps. What did this represent? Number of small candles, number of large candles. You sold, right? You sold 28 total candles. You sold 12 small candles and 16 large candles. Now you might say, well, Mr. Robinson. Yeah, you might say, Mr. Robinson. You might say, Mr. Robinson, you can sell 20 small candles and 8 large candles, and that's still 28. Remember, it's the system. You're not just selling 28 small candles. Yes, you're right. That also gets you 28 small candles. Does that net you $144? No. That would be a different set. Same thing with that, Mr. Robinson. You could have just sold all large candles. You could have sold 24, because 6 times 24. You could have sold 24 large candles. You make $144. Yeah, but that's not 28 candles total. There's only one solution where you sell 28 candles and make $144. This is the only one. This is the only one. And that's what the system of equations is doing here. Number 29. Write a linear equation that represents the area and a linear equation that represents the perimeter of the rectangle. Solve the system of linear equations by graphing. Interpret your solution. Okay. So number 29, we have this figure. I'm going to copy and paste it. Let's write out some expressions for area and perimeter. Now, area of a rectangle is length times width. Perimeter is doubling the length plus doubling the width. So let's just write those out so we make sure that we know. Like that. Okay. So with regard to this system, I'm going to first get it worked on, then we'll clean it up. Here's the thing. I don't know if that means these both represent y. Like y equals y equals. That's the only part that I'm kind of iffy on. Right now I'll write a equals p equals. I'm sure we're going to turn them into y. So that's going to be kind of the weird part. So length times width is here. And that's 18x minus 18. Speaking of which, I'm also not going to show the action of distribution, things like that anymore. You distribute, you're good. So this should probably be a y equals, you know what I mean? But I'll still write it as a equals and p equals and just pretend like they're both representing y. Okay? So 2L plus 2W, 2 times 6 plus 2 times 3x minus 3. Now 2 times 6 is 12. And then distribute there, you get 6x minus 6. So 12 plus 6x minus 6. 12 minus 6 is 6, so that's 6x plus 6. So we have 8x minus 18 and 6x plus 6. That is our system. Okay, that is our system. Blue, green, what have you, these ones that we're going to graph. I guess you treat that as A as a Y and P as a Y. We're finding out, well, it says interpret your solution. So yeah, when we make these the same Y, we're actually going to figure out for what value of X are your perimeter and area the same number. Now, does it matter when they're the same number, really? No. If I get 10 square inches of area and 10 inches of perimeter, those don't actually really mean anything. They're two different dimensions entirely, but they'll just both be the same number. So that's really all it is. Now, I will still use the graphing calculator because of the nature of the area question. So let's go ahead and do that. Let's do 18x minus 18 for area. And 6x plus 6 for perimeter. Okay, I don't know how far I need to go through. Let's just look at this from here. Whoa. Whoa, okay. At least it'll still see it, but if you want to shrink that up a little bit, let's shrink the x's down to I guess 6. I don't need that much, clearly. There we go. Okay. Looks like it's going to be x value of 2 and a y value of something. I forget what my window range was. So 2 and 18. All right, so I get an ordered pair there of 2, 18. Remember, my A and my P both represent a Y, but they specifically represent their areas and perimeters. So what they're saying is when X equals 2, both the perimeter and area, let's see, area and perimeter, will have 18 square units. See, this is the weird part. Hold on, I'll do that in a second. And 18 units. I'll put units and units squared. Units squared and respectively. They'll have the same number, basically. Which is weird, because that, again, doesn't really mean anything. That's what I was trying to do here. That doesn't really mean anything. Oh, they're centimeters. Still doesn't mean anything to have the same. But they do. When x is 2, that's what they are. That would be 3. 3 times 2 minus 3 is 3 for width. So, okay. All right, but that's what it means. That's what it means. All right, let's go to number 30. Thought-provoking. Your friend's bank account balance in dollars is represented by the equation y equals 25x plus 250, where x is the number of months. Graph this equation. I mean, do I have to do it, or is it graphing calculator? Let's see the rest of the problem and see what I kind of got to do here. After 6 months, you want to have the same account balance as your friend. Write a linear equation that represents your account balance. Interpret the slope and y-intercept of the line that represents your account balance. Okay, I'm going to do You know what? This will be fine. I'm going to do this on here. Obviously, I have to change my scale. But if I go by 25s, no, I probably have to go by 50s. I'll go by 50s. So this is 50. So this is 250 right here. And then that makes this 500. Now, every time we increase a month, we're going up 25, which is half the amount. So I'm going to go every 2 months here to get a full, well, no, it's okay. So every 2 months, I go another full 50 on this. So my friend's graph would be like this here. And then this is up 25 over a month, up 25 over a month like this. So I'm hitting halfway points. I can either hit them or not. But what I need to do is I need to make an equation for myself that represents the same thing. Now, your friend's domain starts at that 250 is my guess, represented by the equation there. So I actually should just start it right here and move forward. Now, I need to have the same account balance 6 months later. I need to get this solution for myself in my equation. Now, what dollar amount is my friend at? These are my 50s, right? 300, 350, 400. So at 6 months, they have $400. I need to have $400 after 6 months as well. It says, write a linear equation that represents my account balance after 6 months. I can start with a lesser amount. I can start with, say, 100. If I start at 100 right here, dollars, 6 months later, I need to have 400, which is $300 more. So if I go up 300 over 6, my slope can be 300 over 6, which is 50. And my y-intercept is 100. So I can have an equation that's y equals 50x plus 100. That can be me. So up $50 per month like this. Boom, 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 boom. That works for me. I'm going to go ahead and use that one. Listen, this is open-ended. There's more than one thing I could have done. This is one that just kind of called attention to me. I didn't want to start at 0 because 400 doesn't divide evenly with 6. That means you're depositing cents on the dollar. So I wanted to get something where I'm starting from something else. And that will be my equation, y'all. So that's okay that we didn't use the graphing calculator on that one. Okay, number 31, comparing methods. It says, consider the equation x plus 2 equals 3x minus 4. It says, solve the equation using algebra. Fair enough. And this is where I get to not write any actions. I'm going to subtract x from both sides. I'm going to add 4 to both sides. See how easy that was? I'm going to divide both sides by 2. I get x equals 3. Look how fast I can do that without the other actions in between. I stated what I did. That's the answer. That's part A. Part B, solve the system of linear equations y equals x plus 2 and y equals 3x plus 4 by graphing. No calculator. Let's just do it straight up. They are in slope-intercept form. Let's make it a nice small set in comparison. There we go. All right, so top one's blue, bottom one's green, that kind of thing. So x plus 2 looks like this. If they're going to say which method I prefer, I mean, come on. We know we prefer algebraically. Explain, it's faster. Okay. Now, by the way, I think it's worth mentioning here a couple things, because I don't know if they plan on diving into this further. Why did they take each side of the equation and set y equal to this? And furthermore, how come when I solve the first problem in part A, I only got an x equals equation, but no y with my ordered pair? Well, this is a way that you can solve equations. You can solve not just systems. This is not a system of we made a system of equations out of it. This did not start as a system of equations. It started as just an equation. And you can solve an equation by graphing, by finding the x value where they intersect. Where sure, they get the same y value, but the y value itself doesn't matter for our solution. It just matters that that x value got us the same y value. And that's the x value we're looking for. So when we solve by graphing, what are we trying to do? Sure, is the ordered pair 3, 5? Yes. But what did we want? The x value. That means x equals 3. It's the same answer, right? How are the linear system and the solution? Oh, okay, so they're not asking us to compare. But how are the linear system and the solution in part B related to the original equation and solution in part A? So I might have jumped the gun by showing the x equals 3 part, but you get the same x value for both. Okay? The same x value is obtained in both formats, and substituting that x value into the original equation will get the y value you got in the system. You solved for in the system of equations. So if I substitute 3 for x in here, 3 plus 2 is 5, 3 times 3 minus 4 is 5. You get 5 equals 5. Okay, that's the 5 that comes out here. That's not part of my answer. It is for a system, but it's not part of my answer for this question. That just double checks and shows you get the same y value for both. So why did this set y equal to both parts, both expressions in this equation? We're trying to find the point of intersection, right? They're all interconnected, and this leads into what we'll do algebraically later, of course. You can solve these systems algebraically, not just by graphing. Number 32, how do you see it? A teacher is purchasing binders for students. The graph shows the total. Oh, that's so sweet for them. Sweet of them. I hope that they got reimbursed. The graph shows the total cost of ordering X binders from 3 different companies. Companies A, B, and C. Okay. Numbers of binders and cost. X is number of binders, Y is cost. For what number of binders are the costs the same at 2 different companies? Explain. So with green and red, company B and company C, they seem to intersect, I think, right here. I think that's 20. It shouldn't be, they shouldn't make it too difficult. So I believe they cost the same there. I don't know if we know that actual cost, somewhere between 50 and 75, maybe 65, I don't know. But companies B and C have the same cost for purchasing 20 binders. That's how I see it, at least. They asked me, how do I see it? Now, that was B and C. They all intersect somewhere in these. A and B intersect here. It looks like 35. I'm just going to kind of copy and paste this each time. So A and B will be 35 binders. And then A and C, I think it's out here. To me, it looks like 50 binders. I'm not going to, that's my guess. Looks like 50 binders. That's A and C. All right, that's my part A. Part B, explain, no, those are the points of intersection. Those are the points of intersection for X, right? Those are the X values. The cost is how much they would cost. How do your answers in part A relate to systems of linear equations? Well, they're the points of intersection. Each of these values are the X coordinates. Right? They're the X coordinates of the solution of the, X coordinates. That's a new phrase. Of the solution of linear equations. Now, here's the thing. This is a system of 3. They have 2 variables in each of them, but they're 3 lines. So you can solve a system of 3. Well, here's the thing. These aren't solutions, let's see, of the solution of linear equations for each pair of equations. So here's the thing. This is not a solution. This is not a solution to the system of 3. There is no XY that is a solution to all 3 at the same time. There's only one solution for one set at a time for a pair, companies A and B. Boom, there's a solution. Companies B and C, boom, there's a solution. A and C, boom, there's a solution. There's nothing that's a solution to all 3 at the same time. So keep that in mind. That's why I'm saying for each pair of equations. All right, the last question is number 33, making an argument. You and a friend are going hiking but start at different locations. You start at the trailhead and walk 5 miles per hour. So I'm guessing my equation is y equals 5x. If we're all about systems, I start at the trailhead. That means that's the beginning. Your friend starts 3 miles from the trailhead and walks 3 miles per hour. 3 miles per hour times the number of hours plus 3 miles ahead. Boom, there's my system. Write and graph a system. So I wrote it. That represents the situation. So I wrote it. Let's graph it. Y equals 5x, y equals 3x plus 3. I'll tell you what, I think this is going to go off the graph, the axes here. So plus, let's see, 5x. Oh, wait a second, never mind. This isn't 5x plus 5, it's just 5x. Maybe it won't go off the graph. And 3x plus 3, here's the thing. I don't care about negatives for this one either. We're only walking forward, right? Time. That's pretty thick, though. Time-wise, we're just kind of going this way. So my domain is from 0 onward. 3x plus 3, and it should be continuous. 3, 6, 9. Ooh. So they don't cross out an integer set. They didn't say solve. But let's see what else they ask. Although, we could use a graphing calculator and answer that. Okay, here we go. That's part A. Part B. And last part. Your friend says, after an hour of hiking, you will both be at the same location on the trail. Is your friend correct? Use the graph in part A to explain your answer. No. On part 1 hour, that's X, number of hours, right? X is number of hours. After 1 hour, I will be 5 miles from the trailhead. My friend will be 6 miles from the trailhead. So we will not be at the same place. My friend is incorrect, as they will be 1 mile ahead of me after 1 hour. So that 1 mile ahead, meaning 6 mile mark versus 5 mile mark. It's not until somewhere between the first and second hour that I pass my friend. I meet up with my friend or whatever. It seems like I'm going past them. Like, okay, bye. So anyway, but somewhere in between 1 and 2, it happens, but not at 1. Probably a little closer to maybe halfway in between. I think it's 1.5 because at some point I go 1 mile ahead of them. So it's probably at 1.5 comma 7.5. If I were to use a graphing calculator, that would be my guess. 1.5 hours in, we'd be both at the 7.5 mile marker ahead of time. That's my guess, at least for that one. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. We were indeed solving our linear systems by graphing. We are now going to learn in sections 5.2 and 5.3, I believe, to solve algebraically our systems using the substitution method and elimination method. Keep in mind what we did do in solving by graphing so we can make most sense of what's going on there. Is this frozen? I don't know what's going on there. In terms of what was going on there, like an ordered pair solution and things like that, we're going to use those still. Thank you so much, guys. Take care. I'm going to see you in the next one.